So this morning, we looked at a new kind of a group. We looked at the new kind of group G equal to circle. So the circle is the complex numbers with norm 1. And this is just a group by multiplication inside that. And you can think of the circle as a G, the action, on the vector space. Let's call the vector space equal to the one-dimensional complex vector space, C. And the action of G on V is just, if you take an element of the circle and take a vector in the one-dimensional complex vector space, you just multiply it by the lambda. So nothing fancy. And sometimes in your high school mathematics, we were talking this morning, lambda is in the circle. Since lambda is in the circle, sometimes you write lambda equals e to the I theta, and so, which as you know is cosine. It gets very complicated, cosine theta plus I sine theta. So multiplying by lambda means that you just multiply by e to the I theta times v. And now the circle, when we look at it, just optically, is infinite cardinality. I mean, obviously. Here's the identity, and here's this continuous curve in the circle, but it is a group. And further, so it is a group, and it's an infinite group, but it is a topological group. Because it has a topology, and the topology is the induced topology from lying in the complex numbers. So induced from the fact that it's a subset just of the complex numbers. Very much like the square, but this time this is really a group. You know how to multiply 2 points in the group. If you want to multiply them by angles, here is theta 1, and maybe theta, that's theta 1, and maybe theta 2 is over here. That's theta 1 and theta 2, and then this is lambda 1, and this is lambda 2. Then lambda 1 times lambda 2, you add the angles. I don't know, I'm not very good at the picture. I don't know. Well, I'll close my eyes and hope that I get something right. It's a little bit more, the right angle would be there, so right angle, it would be something like this. No, maybe something like this. So maybe something like this. So this would be the angle theta 1 times theta 2 plus theta 2. This would be lambda 1 times lambda 2. That's a group. There's no problem with that, right? It's just group multiplication of the complex numbers. Okay. Fine, and now we have a situation where we're always looking at the action on functions. So if you have an action, you always look at action on the functions. So let's say associated actions. On function spaces. And you should not look at some horrible function space. Here, we look at the action this morning. I maybe looked a bit more generally. Let's look at the action induced associated action on the polynomials on this vector space. So these are the polynomials. When you write a vector space here with the complex numbers here, these are the complex polynomials on V. Complex polynomials on V. Okay. And of course, if you take, as this morning we were discussing, here I'm only going to take the polynomial algebra generated by the function z. Okay. So that's the function z, and a typical element might be, as an example, for this, let's just have a concrete example, p equals I times z cubed plus 47 times z squared plus something like this. So you have polynomial, here's a polynomial of degree 3 with, it's pretty simple, plus 84, something, I don't care, 84.5. So you have coefficients here are complex numbers. And it's a polynomial in Z. Okay? And S1 acts on that, acts on polynomials. Boy, that's terrible. Strange. In other words, G of a polynomial of, well, let's say lambda of a polynomial in Z is equal to the polynomial, it's the same thing, of lambda inverse of Z. I always put like lambda inverse so that we use left, so we obtain a left action on the polynomials. That's a rather standard thing to consider. And at this point, this morning, I made a remark. The remark I made is that we were talking about averaging here, since S1 is this is the group, so let me write G, which is equal to S1, is compact. The averaging method is available. We talked about this morning. The averaging method is available. I don't want to make a big deal out of it, but I will come very soon to these kind of groups. Compact topological groups, they will even be better than the topological groups. They will be Lie groups, so they will have differentiable structure. But it's not just a manifold, but for now it's just a topological space. But it is continuous, it has many points, it's infinite, but it's a beautiful thing. It's a curve, and it's a groove, and it's compact. Let's remember what compact means. Is you have every sequence has a convergent subsequence. There are many equivalent things to compact, but I think the easiest one for this course is every sequence Zn, let's say Pn, has a convergent subsequence. Let's say Pnk. Okay, so that's the key thing, that we have a compact group finiteness of the group is not so key. The key thing is the compactness of the group. But let's return to finite groups. Of a finite group, which everybody here knows. And this is the example of Sn. And sometimes in any of you German guys know how to write Fraktur letters? Oh, the German, you two guys are German, any other German? Oh, you're German. Can you write a Fraktur letter? Okay, I'll gamble. I'll gamble on writing it. Something like that, right? This subject is very, very German, particularly in finite groups. And the original symbols in this subject were in German. I mentioned this morning of Frobenius and such people. And so when you see, so I was one time, for example, in a restaurant in a town which was trying to be classical, so the menu was written in Fraktur. Do you know the word Fraktur? Yeah, these German letters that you can't read. Well, for example, I'll give you some of them. Oh, well, if you can do Tad, come on. That's what I mean, right? So it's a very, right, so one I know very well. Here's one, it's more or less like this. That's small m. Yeah, some letters like that. And that's Fraktur, this is capital, it's math frac, this is math frac S. So this is Sn, written in the German language. German notation. And what is Sn? Sn, you take the set 1, 2, for example, this set. I have to define the specific group. 1, 2, 3, up to n, this interval of integers. So sometimes I even write this as the integer interval from 1 to n. Maybe I write this thing as the integer interval from 1 to n, in. And Sn, and I'll try to make it Fraktur, I don't know, something like that. Sn is the set of self-maps, bijective self-maps of this interval. So we call those map permutations, you know this, permutations. So let me just say the bijective, so this set of bijective self-maps. You know this. Of IM. So that is clearly a finite, is clearly a group. I hope you agree. If you compose two permutations, you get a permutation. And this is a group by permutation, so it's a group. This is a very famous group. It is a finite group. Everybody knows the cardinality. I think it's n factorial, right? Is that right? N factorial. So as n grows, it's a very big group. Okay. Now we're going to talk about this group a little bit. So it's not fancy. You know, you don't need to worry about it being compact or not. It's just finite. Okay. And now what we're going to do is look at the FC of Sn is the C value. I want to be in C value functions for some reason. I can't help it. I want to be in C value functions. So the C value functions on this permutation. No, on IN. No, excuse me here. I do not want the C value functions on Sn. I want the C value functions on IN. terribly sorry. This is a simple thing. C-value functions on IN. Okay? Sounds ridiculous, doesn't it? C-value functions on IN. Now, you physics people, I'm going to excite you now. So it'll be very exciting. There are special functions that are very nice. I call these functions the Dirac function. You always have these Dirac functions, but these Dirac functions in this case make very good sense. These Dirac functions, I'll call it delta x for Dirac functions. It's equal to 1 delta x of I don't care s is equal to 1 if s is equal to x. It's 1 if s is equal to x, and 0 if s is not equal to x. That's delta x, Dirac function. 1 if you would write this thing, here's 1. Well, this is a function on I. So here's 1, 2, up to n, and someplace in here is x, and this function is 1 at x, and 0 otherwise. So you know what this function is. It's called Dirac function.
It's not function, right? Is it function?
Who's speaking?
Me.
It's a function. I'm glad you asked the question because, so it's a function. It's a function which associates to, I draw its graph. People draw it like this. It associates to x the number 1, and otherwise it's 0. You agree it's a function. It's a rather stupid function. Yeah? Okay, but nevertheless, the way you should think, you have all these Dirac functions. This function space, this is a vector space. Right? If you can add two functions, it's a complex vector space. And these Dirac functions, every function, well, if you have any function, it's a linear combination of the Dirac functions. So I'll write it like this: Zi Dirac function I. Isn't it true? Isn't it true? This function, so if I multiply Dirac function at I is 1, so that means this is a function. Let's start writing. F at the point 1 is Z1. F at the point 2 is Z2, and so on. So it says that F is a linear combination of the Dirac functions, right? Dirac functions. So if you have these, if you have 1 through, where did it go? 1 through n, I don't know, oh, here it is. This interval I, n. Where the heck did I write it? Oh, there it is. 1, 2, 3, 4, 5, 6, 7, and so on, up to n. I have the Dirac functions for each I. So a general function is of that type. This then says that the Dirac functions, delta 1 through delta n, are a basis of that vector space. Every function is a linear combination of those Dirac functions. I just wrote it down. Every function is a linear combination of the Dirac function. Right? Okay. So in that sense, if f can be written down in this way, z1 through zn. This is a hysterical justification of this business because we did it in a basis. But it's a very natural basis, by the way. This natural, I think, the Dirac basis of, don't you agree? I mean, it's sort of a natural basis of these functions. Right? So every function is just written like this. So this means in this basis, Z1, Z2, Z3, the basis is the Dirac stuff. This means, by the way, I'll tell you a story. My good friend, and when I was a student, maybe probably I'd say a little bit older, at some university in the United States. My office mate and my good friend was named Wigner. And his father was named Wigner, and his father was the famous physicist, Nobel Prize winner and great discoverer of many things, named Wigner. So my friend was named Wigner, and he was getting his doctor's degree at the same time I was. We were friends and in the office. And his uncle's name, whom he also had known to a certain extent, was named Dirac. So it's very interesting. You may not, can you imagine this poor guy was my office mate, his father was Wigner, and his uncle was Dirac. Yeah. But he was a mathematician. My friend became a mathematician in France. I've lost touch with him. He was a mathematician, a well-known mathematician in France, whose father was Wigner and whose uncle was Dirac. His name was David, so David Wigner. So anyway, this means that 1 goes to Z1. I'm telling you what this is as a function. 2 goes to Z2. 3 goes to Z3, and so on. This is a function. So it's a mapping on functions. And now, if you have a permutation, of this interval, then f, so sigma of f is f composed with sigma inverse. This is the way you make it a left action on that. And in fact, this means that sigma of this vector, if you want to write it as a vector, is equal to z of sigma 1 inverse, and so on, up to z of sigma n inverse. Sigma inverse of n. Again, you're putting the inverse in there to make it a left action. Just don't worry. If it bothers you, don't worry about it. But you put it in there to make it a left action. Okay? So it says that the action on functions amounts to this. Yes? You're going to think I'm crazy, but what we're going to do now, you see what we're having? So this is what we have. We have an action on the vector space V, which is the space of functions on the interval, which is C value. I'm beating their heads on this because it's a confusing point, and I want to do it cleanly. You started out with the interval. You have the action of the permutation group on this interval of integers. That gives you an action on the vector space of functions. And now when this is a linear representation on the space of functions. Linear representation on the space of functions on V. And if you have a linear representation on V, then you should go to the associated representation on the polynomials. On the polynomials of V. Is that confusing? Okay. You have a finite set. Somebody was telling me he likes combinatorics, so a finite set is a combinatorial object. Right? You have a finite set, and you take to be 1 through n, finite interval, and you look at Sn, the permutation group on this. It's a big finite group. To understand a group, you look at spaces of functions where it acts on IN by permutations. So you look at space of functions where it acts. That's a vector space. If possible, you can find, this is dedicated to Prabhupada because he likes to tell me historically we'd have a basis. Here we have a canonical basis almost. It's really funny, right? The Dirac basis is essentially canonically associated to this. So you have a standard basis. Every function is a linear combination of that basis. That means really a function is given just as a vector. That means this. So it means that this function space is the space of functions on IN is this vector space, which is Cn. Now, if you want an argument for studying high-dimensional mathematics, yes, if you take, I hope you understand that it appears in. Let me make a remark with these computer science guys sitting here. Yes. Stupid mathematicians think that you can write a loop in a computer program to compute n factorial. Well, you can write the loop. Well, even I can write that program, n factorial, right? You write a loop, right? So n factorial. Can you? I don't know. You have some computer science person. Maybe one of you guys can tell me. N factorial. Let me take 1,000 factorial. Right. I don't know how much time it would take on a quantum computer to compute 1,000 factorial. I'm not sure. I'm not sure. There would be also round off. I mean, there's really a major problem computing big factorials. Do you understand that? Nobody computes big factorials on a computer with some loop. Right. Right. Nobody does it. You do it with you do it with Stirling formula or something else to compute. It is completely ridiculous. No human being computes on a computer some big n factorial. As far as I know, you don't do it. That's one of the problems if you're doing probability theory and you have things like this, n over k, and you have binomial expansion and things like this. You were very happy to talk about asymptotic distributions, for example, a Gaussian approximation to Bernoulli distribution or something. So you don't want to do that. So, but in any case, let's just look at this. I mean, just for fun, for n equals 10, you're talking about some trivial combinatorial problem with n equals 10. I mean, that's a small number. I don't know what, does anybody know what 10 factorial is? I don't know, just for fun. I don't know. I don't know, I'm not very good. 24 times 30, I don't know, but I don't know. This is some astronaut, for me, a huge number. Do you understand? You immediately are forced to look in Cn, where n's that big number. Right? You can't stop with some Mickey Mouse number. You have to go to some big number, even if you start with the number 10 here. So it's a big argument for doing that. And then after you've done that, these functions, you look, this is a natural space where this group acts. Then you look at the space of functions on that space. 2 times we've done functions. So we look at space of functions here. And this is a polynomial, and I'll write it on Z1, polynomial Z1 through Zn. This is a polynomial of n variables. And now sigma of this polynomial of Z1 and Zn is equal to P of sigma inverse of this vector. And that's, as we know, it's very interesting. These 2 inverse operations cancel. That's Z of sigma 1 through Z of sigma n. So maybe you're seeing too much notation. You understand what happened here? We did twice in some sense the functions, and so you take sigma inverse of something, and we notice if you apply sigma, you get a sigma inverse. So when you apply sigma inverse, you just get sigma. So I hope you understand. Yes,
But in that notation, isn't it then saying that the polynomial is a function or a map which maps some function in our...
Yes, twice functions, actually.
Okay, so it's a polynomial of which we apply to a function
Mhm.
in the end.
So, it's a confusing thing. I know where you're confused. I'm just going to try to answer your question by restating what I said, okay? You have the interval, In. You have the permutation group acting on the interval. You have the idea of let it act on functions. Right. A function in this basis is a vector, z1 through zn. Okay? That's how, it's a vector, it's a point in Cn. Okay, that's how it acts on C, as a point on C, is a point in Cn. Okay? Maybe that's the confusing thing. Okay. Okay. And now, as the action on that as a point in Cn gives the inverse, sigma, I wrote it here, is that. That tells you how it acts on that tells you how it acts on Cn. Geometric action. Okay. And now if you look at polynomials on Cn, you see, if you look at polynomials on Cn, there's sigma the polynomial. I'll just write here z is equal to the polynomial y to sigma of z, sigma inverse of z. Just keeping left action straight every time. It's a screwy thing, but it really makes life easy to get it right, because I hope you understand. Do you remember anything about notation? Suppose this is 1, 2, 3. So let's do this n equals 3. Right. Do you know what is meant by line notation of a permutation? 2, 1, 3, no, make it interesting. 2, 3, something like that. Let's say that. Do you know that notation? Are you familiar with so-called line notation? It just means 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay. So let's say that's sigma. So you don't even need this thing. So 2, 3, 1. So sigma is 2, 3, 1. All right. So okay. And so you take the monomial. For example, p equals z1 to the 17, z2 to the 8, z3 to the 5. Some horrible monomial. You understand? If you just have something blocked in like that, it's a we call that a monomial. Monomial. All right. So sigma of this monomial is, okay, 1 goes, where does 1 go? 1 goes to 2, so it's z2 to the 17, 2 goes to 3, z3 to the 8, 3 goes to 1, z1 to the 5. Does everybody get it? This is the action on monomials. That's all you need to know, because the action, okay, that's how the action is. Okay? Okay. Okay, good. Now, we have the situation, we have our situation that I want to study here, and we'll study it carefully, is this. We have a linear representation of Sn on Cn. I'll review the thing here. A permutation of a vector is equal to, if you do it right, you actually should write sigma inverse here. It doesn't matter too much. And then you have the induced, associated, I say induced all of it, associated representation on polynomial. Associated representation on polynomials. on polynomials. And that is all of these guys. And that is sigma of a polynomial at a point z1 through zn as a function is equal to the polynomial then at the point. Okay. And see the above example. Okay? It's really interesting. Yes?
Why is there in one case sigma to the -1 and in the other case is just sigma?
And, you know, I have trouble hearing, so I have to come back.
So why in one case you have sigma to the power -1 and in the other one you just have sigma? Does it matter?
Yeah, I thought I explained it, but probably not. She's asking, it is confusing. At one point, starting with the interval in, we have a representation of the permutation group on Cn. I regard a point in Cn as a mapping from the interval I1 1 through n to the complex numbers. So when you have the action on a mapping, to make it a left action, you have to have sigma inverse. That is the reason on basically the third line on the left board there. This has given us a representation of the group on Cn. Now close your eyes. Oh, she did, she closed her eyes. That's a representation, which is very natural, I mean, it's very, right, of the permutation group on Cn. And now we look at the associated representation on functions on Cn. Yeah? And as soon as you, yes, go to the associated representation on functions, you have to apply the inverse inside the function, and inverse of inverse cancels the inverse. Okay? That is why when you do mathematics quite often, you can't believe it, but you're very lucky that the action on polynomials, for example, on this monomial, it's what you do. You just have the index here, 1, 2, 3, and 1 goes to 2, so you just put 2 there instead of 1. 2 goes to 3, so you put 3 there instead of 2. 3 goes to 1, so you put 1. It's the easy thing. You don't have to worry about inverse. Okay? It's nice, yes?
What does the term representation mean?
Okay, so I said it in words, and I'll say it again now, precisely. So, Mr. Weiss is asking what the devil does the word representation mean, okay? And so, oh, I think I should go over here. So I'm going to be talking about a representation. Implicit is the word linear. Representation of a group G on a vector space V. That's what you're asking. What the devil does that word mean, representation? Very easy to say. This is a G action. A G action by linear transformation period. That means G of AV plus BW is A G of V plus B G of W. right? So it's a G action by linear transformations, and by complex linear, these scalars are for me in the complex numbers. I prefer complex numbers to you. So this is a complex vector space. It could be any vector space, it could be over some field, it doesn't matter. But here I made it over C. Okay. So in other words, the way you should think, there is a map of G to GLV, which is a group homomorphism. It takes G into, it's a group homomorphism. This is equivalent. Okay? And I wanted to write the second definition because, as you know, GLV, this is GL, like C of V, can be regarded as a space of matrices, which has a topology. And, obviously, it's just matrices. And quite often, if this is a topological group, a group with its own topology, this map should be at least continuous. Now, for those of you who heard some words, if the group G has differentiable structure, this should be differentiable. So if it has differentiable structure, the word is Lie group. So if it's a Lie group, this should have differentiable structure. If it's a complex Lie group, which means it has a complex differentiable structure, this map should be holomorphic, and so on and so on and so on. It should be, so the group itself should maybe has properties. The actions should also be properties, have those properties. He said, structure preserved at the level of the group. Okay. Linear representation. Linear representation. And so quite often we don't say linear, we say representation. Okay. So just for fun, recall that the dihedral group is acting on R2 by, and I'll emphasize here, this is a real vector space, real linear transformation. And the reason it's not complex linear is reflections are not complex linear mappings. Rotations certainly are, but reflections are not. So the rotation subgroup is okay. It's complex linear, but this is acting by a real linear transformation. Is that okay for your definition? Thank you. Okay, so we have a wonderful thing here. We started probably with the most obvious finite group that there is, namely the permutation group on n numbers. And we are led to study, study the representation of the symmetric group. This is called the symmetric group of permutations on C, the polynomials of V, where V is Cn as above, And I would like to study that just a bit. So I would like to give you an example of something very interesting. how does Cn appear Cn appears in the following way. And that's the reason I'm taking over the complex numbers by the fundamental theorem of algebra. It occurs in the following way. So this is very bad didactics here. Cn appears in the following way. Yeah. If you take a polynomial in one variable, z, one variable, I don't know, let's call it q of z, because it's not the same p as before. Q of z, some polynomial in one variable, it's important in one variable. The first thing you do in school is you say, this is a product, z1, z times z1. Somebody told you that Gauss or somebody proved that this thing factors into a product of linear polynomials in one variable. Everybody agrees, I hope. It's called the fundamental theorem of algebra, right? Every polynomial is, you can factor it into, and then you ask somebody, what about this factorization? No, you tell somebody this. You tell somebody in a foreign country who's blind, it factors into a product of linear polynomials of that form. This person won't be able to do it. He's worried very much about the unicity of that factorization. That factorization has an order in it when you write down on a board like that, right? First root, second root, third root, fourth root, fifth root, sixth root, seventh root. There's no such thing as the first root of a polynomial. Well, maybe the smallest, but these are complex numbers or something. Right? There's no such thing. So as the Germans say, that's Quatsch. That's nonsense. Right? There's no such thing as that ordering. If you choose an ordering, there are such a thing. If you choose an ordering, right? But then you say, well, let's multiply it out. If we multiply it out, there's a monic polynomial here. I always like to choose a monic polynomial. Z to the n. Now there's going to be a sign that we're going to have to take care of here. And I'm going to worry about the sign later on. I'm just going to say plus or minus, I can't remember. C1, coefficient 1 to z to the n minus 1. I don't know about the sign. Later on, I don't know. Coefficient 2, c to the n minus 2, c, and so on. All these coefficients times c and cn. Right? And if I write it like that, those coefficients are well defined as a function of the polynomial, right? Yeah. These coefficients are well defined. Now let me see. C1 is equal, I'm going to write C1 is equal to the sum of the roots. Now, you know, I just lied maybe. I said the order, I wrote down those roots in order, but the sum of the roots, it doesn't matter on the order, right? You agree? It's well defined, independent of the order. You agree? So even though this is quatsch to write these things down, there's no such thing as the first root. This makes sense. Now probably then, if this is probably, oh my goodness, I don't know. There's some number here in front of it. I don't know, whatever. Can somebody tell me quickly if that's a plus or a minus? It's the coefficient of, Uh-huh. Well, I don't know. C1. Did I write that? Is that correctly? Is that correct? So it's, for example, you take, oh yeah, that's correct. It's the standard blah blah. You take n minus 1 z's multiplied by one of the zi's, right? Well, I hope you can do this. I hope you can do this. You've never done this? I don't know. It's z to the n, and then, I don't know, plus n minus 1 z's. Oh, it's minus. N minus 1s of these z's, and now you take them from the first n minus 1 terms, and then so notice take them from the last, so it's z1, and then take it from the next to the last, and so on. So this is okay. So what did I say it is? It's minus. All right? And now what is this? C2, it means you take two of these guys someplace, right? Right? Z1 and Z2, and then take the rest of them to be Z's. So this is going to be plus. Okay, it's going to alternate now. So this is Z1, Z2, and all possibilities here. Plus, you know how Z1 is Z. This is going to be terrible. Z1. No wait. Z1 squared. You don't get it. Z1. Z3 plus Z1 Zn, and then you know how to write these things systematically. And now Z2 Z3 plus Z2 Zn plus and so on, right? Plus Z, and then at the end you have Z minus, you have this. Is anybody objecting to that? That's okay, right? That's what you get. So this is a terrible thing, and then that's plus, and then, the last one's pretty easy, right? Cn is equal to, I hope, let's get the sign right, all the products. Oh, it depends, right? It's the product of all those roots, and it depends. It's minus 1 to the n, I think. Isn't it minus 1 to the n? Cn, and Cn is Z1 through Zn. Is everybody cool with that? Notice that these things are polynomials. These things are polynomials. All of these things are polynomials in n variables, and these are polynomials in the polynomial ring on the vector space that we were just talking about. Right? The vector space we were just talking about is a ring of polynomials on Cn, where Maria asked me this question about sigma inverse and so on. That's where these things are. Okay? Yeah.
But in that notation, it's not possible that we have something like C1 to the n or whatever.
No.
So it's not the same. Or is it?
Well, what do you mean? Not
Oh,
the same?
okay, yeah.
I didn't say it was all the polynomials or anything.
Yeah, so they're in there.
He said in that notation you don't have Z1 squared or Z2. You're absolutely right. I'm going to talk about that in a minute. Okay. But at least we have these n functions. Okay? And these n functions, C for coefficient, and for those of us who like vector bundles, these are the Chern classes. These are very closely related to the so-called Chern numbers of vector bundles. Just forget what I said. You don't like that. I'll tell you sometime. You come to my office, I'll tell you what, it's very nice. Okay. And the key is, not only are they polynomials in Z1 through Zn, they are The numbers 1, 2, and so on are good, because this is a polynomial degree 1, this is a polynomial degree 2, this is a polynomial degree n. That's nice notation. And the point is, these are invariant. It's obvious they're invariant just from the formulas, but it's obvious because they're roots of a polynomial. And you put these symmetric functions in the roots of a polynomial, they have to be invariant, right? Okay. These things are called the elementary symmetric functions. And I will denote them by, S, by C, because I like what I said about vector bundles, but you will see them sometimes denoted by S1, S2, S3, and sometimes. Okay. So I gave some lectures recently here in Bochum where they were called S. So sometimes denoted by otherwise by S1 to Sn. Okay. These are called the elementary symmetric functions. Okay? And now we have a new idea. You see what we did here? What do we do here? We started with a function and we averaged it. We started from a function and we averaged it. You agree? Well, I didn't quite average because I didn't divide by the number, right? But I averaged it over, isn't that what I did? I added up exactly this time yesterday. I talked about the averaging operator. So before I say a new idea, let's say, what is this in the lingo of, so C1 is the average of the function Z1, C1. And C2, this coefficient 2 is the average of the function up to a number. And sometimes the number is important. Maybe I should divide by the order, but I'm not going to worry about it too much now. This is average of the function Z1, Z2. And so on. And of course, the last one you don't have to average it, it's already invariant. The average is Z1 through Zn. So, look what we did. We started with a permutation group. Everyone in the room is completely satisfied that that's an important group. We got the natural action on polynomials. We want to find the invariant for a good reason. We want to find the invariant, the things that are really invariant don't depend on the order of the roots, for example. And our idea is to take the obvious things, the linear monomial, the obvious order 2 monomial, and so on. But here with mixed terms, everywhere, you understand? We take the next, well, all right, let's write right here. C3 averages C1, Z2, Z3, and so on. Cn, you don't need, as I said, you don't need to average this one. These are the elementary symmetric functions. Every mathematician, every physicist, everybody in the world, every computer science needs these things. These are the basic invariants of the permutation group. So the new idea I started to say, new idea, and is to start with different functions. And I'm going to call this one big N because everybody calls it big N. N1 to be the average of A1. But N2 to be the average of z1 squared, and 3 to be the average of z2 squared, z1 cubed, and so on. So in the table that I did, comparing the two tables, n1 is equal to the same thing. N2, well, it's a different configuration, is the same thing but with squares. All the way down to n and n, which is the z1 to the n plus zn to the n. Okay. So you pay your money, life is capitalistic, you pay your money, take your choice. You start with these interesting monomials z1 times z2, z and so on. You average those. Or you start with, this is what Mr. Wise was worried about when you were asking me before. Here I'm starting with z1 squared, z1 cubed, and so on. I just average them. Okay. All of these things are invariant polynomials of the symmetric group and are clearly very, very important. Also in physics, let me say, well, eigenvalues are some of you have experience with eigenvalues of a matrix or of a linear operator and their energy levels of a certain thing in physics. Yes? And of course, they are not well defined because the order doesn't matter. Yes. And so what's really well defined are these things. These are the really physical invariants of anything, of any polynomial. So the polynomial I'm talking about in physics is a characteristic polynomial. So these things have a name. These are called n, the word n is, the letter n is okay because these are called Newton polynomials. And that, I think that would be a good notation for Newton polynomials. So there are two kinds of basic invariant polynomials. And let me state a theorem, and I will try to prove this theorem. The symmetric polynomials what did I call them? C1 through Cn generate the invariant polynomials all the invariants that you get here from the symmetric group. I've intentionally written this in a little bit of a vague way so that you pin me down on what it means, generate. They generate that. So, you have to understand what that's going to mean. So I'm going to say, i.e., I have to get this, i.e., the algebra of invariant polynomials with respect to permutations is simply the algebra generated, that means the polynomial algebra in C1 through Cn. That's what I mean. That's what I mean. Oh my goodness, was she mad? I think she just had to hurry. She's going with the wind. It is the polynomial in algebra here. What that means, if you have any invariant polynomial by the symmetric group, then this polynomial is some polynomial of C1 through Cn. You got it? This is really a theorem. It's invariant theory. Think what we're thinking about. We have group action. We're looking at the quotient by the group. Therefore, we're looking at invariant functions. I write down the most natural invariant functions which come from looking at roots of polynomials. Also, these are very natural, these Newton polynomials. You write them all down, C1 through Cn. These are very natural things. And the statement is, that's it. That's it. End of story. Every invariant polynomial is a polynomial in these things. You can't do any better. I hope you understand what I mean. So for example, for n equals, I don't know, for n equals 3, that's on C3. So we have the, how many n equals 3? So we have these invariant, we have the symmetric function z1 plus z2 plus z3. And we have the invariant function as z1, z2 plus z1, z3 plus z2, z3. And we have the invariant function z1, z2, z3. Okay? And it means that if I have a polynomial p, which is invariant of these things, an invariant polynomial as up there, say of degree 4, that's fun. An invariant polynomial of degree 4, that means it's a polynomial in these variables, and here's something at degree 3, and here's something at degree 1, so it would be some coefficient alpha times the polynomial of degree 1 times the polynomial of degree 3, which is this, z1, z2, z3, plus beta times polynomial of degree 2 times itself. So z1, z2, z1, z3, z2, z3 squared. Isn't that the only way you can get 4? 2 times 2 is 4. Oh, no. 2 plus 2 is 4. And 1 plus 3 is 4. Right? Did I miss anything? Those are the only possibilities, right? So I don't know what alpha and beta are, but if you give me P4, I know it looks like this, and usually I can compute alpha and beta, right? It's what is called comparison of coefficients. So, yeah, that's really a wicked theorem, that you have this basis of an invariant polynomial by symmetric functions. And by the way, the same thing is true of the Newton polynomials. The Newton polynomials is the Newton polynomial. The invariant functions on E of the symmetric group is the polynomial algebra in the Newton polynomials. Newton 1, Newton 2, Newton 3, up to Newton n. This is also extremely useful, extremely important in mathematics. I'm sorry. And now let's see, for example, P being 4, then let's see, we need the degree 2. First of all, we need 1, 3, so it would be alpha hat times, well, that one's the same. The first Newton is the same as the first symmetric. And then I have to have the one Newton of 3. So Newton of 3 is z1 cubed plus z2 cubed plus z4 cubed, z3 cubed, plus beta hat Now what do I do? I need the Newton polynomial of degree 2 squared. So z1 squared plus z2 squared plus z3 squared squared. Yeah? Yeah? That's very interesting, I feel. Yeah. The Newton polynomials and the elementary symmetric functions are more or less standard canonical generators of the invariant functions. And those are the functions on the quotient of this vector space modulo the symmetric group. And they are determined by averaging. Okay. Now I want to have a small proof of that.
Just a question.
Yes. I make a mistake?
No, no. So m equals 3 is operative. You could do this with 2 or 1 or 5. So
I could do it with anything, yeah. I just chose 3, whatever, I don't know why I chose. Yes,
you
yeah,
can do with 2.
whatever, yeah. But if n equals n,
Yeah.
then the polynomials run up to, the invariant polynomials run up to degree n. Okay, yes.
Couldn't we also have a term such as the term of order 1 to the power of 4?
Oh, I forgot that. Yeah, I just forgot it. That could happen, why not? 1 to the 4th I forgot. Is that the only one I forgot? Alpha, beta.
And you could also have something like the term of degree 2 plus the first term of n to the power of 2.
Wait a minute, let me put the term of degree 4 here. Maybe I forgot a lot of terms here, I never know. So you say term of degree 4, so you take this thing to the 4. That's what you just said. Is there anything more?
And now the c1 squared times c2.
Oh, yeah. Alpha, beta, gamma, delta. C1 squared. So this one, I'm glad you were thinking with it. This thing's squared times C2, which would be this. Yeah, even here, I mean, even in this very small thing, it gets really hairy, right? I mean, okay, Z1, Z2, Z3, no, Z1, Z3, Z2, Z3. Is that it, Nicholas? That's it, right? So I have to do the analogous things here. I won't do it alpha, whatever it is. Yeah, yeah. You just have to put things so they add up to 4. It's not hard. I can't do it. I'm so stupid. But okay. Yeah. Okay. That's really interesting. And so this is one of the first results in invariant theory, and I'd like to try to give you an idea of its proof. Now, there are many proofs of this fact. This fact is completely classical, as you see the name Newton. but I want to give you an idea of a proof. In the spirit of quotient theory. And again, if you're interested in this subject, this would be a very nice little paper you could write up, fill in the details of this and take a look at various other things. We start with the vector space Cn. And the action, which is a linear representation of Sn as above. In the notation of our course, this is x. We've been talking about g actions on x the whole time. I mean, this is x. I always draw the picture x upstairs, and the quotient, this is the group G, and the quotient x modulo G downstairs. Here we had earlier the continuous functions on x. Here we had earlier the continuous functions on x modulo G. Continuous functions in life are much easier to understand than polynomials. They are much more complicated, but in terms of conceptual properties of continuous functions, they're much easier to understand. And we know here, in a very natural way, that the functions on the base are the same things as the invariant functions on G invariant functions on x. And we know you can make G invariant functions, so, and we know that the averaging operator, A, is a projection of all of the functions, continuous functions, onto G invariant functions. Remember what A is. A of F is the sum of G of F divided by the order of the group. I didn't divide by the order of the group when I had made these functions, but it's just a matter of scaling, so I don't worry about it. Here we're summing over the group. Okay. Now we have another construction. We have x. We have x. We have x. In our case, Cn. And we have another construction by a map, which I'm going to write down. F is, I'll call it C for coefficient map, C1 through Cn. This coefficient map also to Cn. Yeah. This is an example of an invariant map. Right? So it means that there is a map. So here we go. That we have. Let's see here. Let's look at it this way. we have a map from X over to Cn by this mapping C, and we have a map from X to X modulo G. This is invariant map. This is the canonical invariant map. This is given by invariant functions. This is certain invariant functions. Maybe not all. But therefore, it factors this way. Do we need to discuss that? Maybe. Yeah.
How does C act? Is it just that we represent the point in the basis of C1 to Cn?
So it's very interesting to try to understand this in detail. I'm not sure what your question is. Say it again, please.
How does C act on Cn?
How is this? No, this is the mapping C.
Yeah.
This is the mapping C here. So what I mean by this, let me give you an example of what I mean by it. Well, it's very easy. If n equals 3, as an example, okay, it's very interesting. If n equals 3, then we have C3, point of C3 is given by Z1 through Z2, Z3. Right? That's a point of C3, and it gets mapped by this mapping C to Z1 plus Z2 plus Z3, Z1, Z2, Z1 plus Z1, Z3, plus Z2, Z3, and finally Z1, Z2, Z3. Okay. Okay. That answers your question. I wrote down the map in 3 variables. So it's the map given by the 3 invariant function, what do you call it? Simple, no, what do I call them? What do they call it?
The symmetric polynomials?
Yeah, the symmetric polynomials. If you have 3 symmetric polynomials, you get a map to C3. Right? Yeah, Martin's got a question back there.
I suppose the question is, why can this then be identified with C3?
You're too quiet, Martin.
Why can we identify this with C3? How do we know? I think that's the part where at least I'm not seeing. Why is this the whole of Cn?
Okay, this is very good. Okay. So I didn't say here. By the way, I didn't say that is the whole of Cn, but you're absolutely right. It is the whole of Cn. So Martin's asking about. We better understand this mapping given by the invariant functions or by the Newton polynomials, right? Say going to C3 is enough to understand. C1, C2, C3. Okay. Yeah. I know that for various reasons. So he's asking the question, why is this map to all of C, all of C? So the 2 properties of this map, that's one property. So let's call this mapping C. So the properties of C. So as Martin's pointing out, I know for various reasons this mapping is surjective to C3. Surjective. And, well, subjective, and let me just say properties of C, let me call it, mean that this mapping is invariant. This mapping is invariant, and that establishes a mapping from the full invariant quotient here. So this mapping here is a topological isomorphism. And it is sufficient, as Martin is pointing out, to prove that this map here, C separates orbits, it should, and is surjective. Okay? And I know why that is true for me, and I'm trying to see if I can prove it in elementary terms. I thought I would be able to give you a very elementary proof. But maybe I can. Let me just think for a minute. The main point, by the way, is the surjectivity, as you're pointing out. The surjectivity then of C. Well, let's see here. So, let's see, we have an orbit upstairs. We have an orbit upstairs of the symmetry group. That's an orbit. Right? And we have a point downstairs in Cn. And now, if I take a this is an orbit. So this is on the symmetry group. Let's do it for 3 letters. Oh no, that's already very big. So the orbit of the symmetry group. Yeah. Let's see here. And we average, what I'm thinking about, if we average the number, no. Actually, I don't see it by elementary means anymore. Marta has a very good question, right? Why is this map surjective? Okay, I'm sorry, I don't see it by elementary means anymore. I see it only by algebraic geometry. Okay.
Usually there's some sort of...
Or do you see it by elementary means?
I think I recall seeing some sort of induction argument.
Yes, but the point is, Martin, you're absolutely right. If you look in some book, right, there's some stupid argument by induction that has nothing to do with this situation, right? And you need to show that this map is surjective. I think you can show it by elementary means. Right now I can't see it by elementary means, okay? But I want to prove this thing by some method I don't want to just give a new proof, but by a method, you see, a proof by induction doesn't tell you anything, right? I want to prove this theorem using something that tells you something. And I think we can prove by elementary methods. So, properties of C is that mean that the mapping below, mapping, this mapping is an topological isomorphism. So for those of you who are not so interested in this, as we are, Martin and I are interested in this, other people also interested, but maybe not as much as we are. Just accept this for a minute, okay? Okay? Okay. Suppose that I'm wrong. Suppose that, in fact, there is another invariant function that I missed here. Do you get what I'm saying? There's some other invariant function here that is not in this polynomial algebra. Okay? Suppose I'm wrong. Suppose there's some other invariant functions. So suppose let Q be some other invariant function. That means we have another map which is C together with Q, which goes to some other set which I will call Y. I can see now I am using far too much algebraic geometry in this proof. Yeah? Which of course factors here. So I'm terribly sorry. Yes. But since this thing is really the topological quotient, this mapping has to be bijective, because that would mean that this is also the topological quotient. So that means that this map is bijective. Okay. If this is the topological quotient, we add another invariant, then this is also the topological quotient. You can't change anything. Okay. This will be also the topological quotient, and we will get a map from Y to this space, and we prove by algebraic geometry that this is an isomorphism. And I wanted to give you this proof. It's a beautiful proof, and it reflects really what's going on. Let me just say, you first show that these things do the right job for continuous functions. That means if you have any other invariant theoretic quotients by polynomials or anything, it doesn't matter, that this map here, this is a better map, so to speak, and you get this map here, that this map here has to be bijective. Because this is already giving you the topological quotient. This map has to be bijective. This means this separates orbits and so on. This has to be bijective. And we were drawing a lunch about this result. We used the fact of algebraic geometry. Under certain conditions, if you have a bijective algebraic map, it is an isomorphism. I mean, you go, ugh, but it's a serious thing. There are conditions. The base has to be normal. The upstairs space has to be irreducible. So this is a very important basic theorem I wanted to implement. Yes.
So the terms topological isomorphism means that it separates orbits.
Yes. So you see, that's the kind of that's exactly the point. So.
But so which orbits does it set? So basically.
So yeah.
I mean, we have 2 points in the quotient, and
Yes.
then they get mapped to 2 different orbits. I don't know.
No, it's the other way around. This is the easy part to prove, the separating points, which you can prove yourself easily. You have 2 points in the quotient,
Mhm.
and you want to get a map over here to this CN, which is the image by the symmetric functions.
Mhm.
Take 2 points in the quotient. These are 2 orbits up here. You have to find two symmetric functions, which a symmetric function which separates those 2 points. And that's very easy by averaging technology. Okay?
Mhm.
The point is, what Martin made me mad about is, why is this mapping, you want to control that the image of this mapping is something reasonable. I don't even really care in general, but this is not affine variety in
It
general.
is.
Huh?
X is an affine variety in this case.
Of course, X is CN.
So we have an open map, so
No, it's not so obvious. No, there's no such thing as an open mapping theorem in algebraic geometry. No. So there are various reasons, this mapping is proper is the reason it is. And, okay, so don't jump too fast, Marty. But it's mapping properties in algebraic geometry that tell you that this mapping here goes on to CN. Okay? We talked a little bit about it in the complex analysis course. For proper mappings, this mapping is proper, so it's surjective. So you need to check that this mapping is proper. Okay? Proper means if something goes to infinity, then upstairs, okay, proper mapping means proper. That's all there is to it. Yeah. So you have to invest more technology. I'm almost sure that it's trivial to prove this with elementary methods that map is surjective. Okay? You understand what I'm saying? It's a stupid question. It's a question that anybody here can start to ask. And maybe it's, you understand, I mean, all these talking about proper mappings, is all nonsense. But you have a map from CN to CN. It's an interesting exercise, given by symmetric functions. Right? Why is that surjective? Yeah? I think you could probably prove it by elementary methods. I thought about it before coming here, and I thought I had it, but I've forgotten what I wanted to say in the proof. And my trouble is I know too much. Yes? And then Martin's trouble is he knows too much too, but then he starts making stupid remarks like it's an open map. But he's a good guy, I like him. Right? Yeah, it's a danger. Martin and I have talked about this. It's a danger to know too much, right? You have to think, yeah? And you're better off because you don't know anything. You can just check it. Maybe you understand what I'm saying. You just check it's surjective. And then as soon as you know it's surjective, you're really done. Because if you have some better thing, then you get it's very easy to see that this is a algebraic variety, and you have a bijective map between 2 algebraic varieties with certain qualities. And this is one of the basic theorems in mapping theory. That mapping is an isomorphism. Okay? Maybe not so obvious. Okay, I know many of you were bored. I think maybe I've said enough, but it's a very interesting thing. I think to write a little paper on this would be very interesting. And now, by the way, a challenge for you people, for everybody who just for fun, to end today's lecture. Every Newton polynomial can be written as a function of the symmetric polynomial. It says the symmetric polynomial is generated. So every Newton polynomial can be written as a polynomial in the symmetric functions, right? And every symmetric function can be written in a polynomial of the Newton functions. Do you understand what I'm saying? I challenge you to write a formula. Now this is something, maybe you program you can program a computer to do this. So it says they generate every function. So the first symmetric function equals the Newton function. The second symmetric function is some function of the Newton functions. I don't know what the function, I'll write them all down here. F2. The third symmetric function is a function, so on the nth symmetric function is a function of the Newton polynomial. You guys are much smarter than I am. Let's try one. Okay, let's try it. What would you like? Let's try 3 variables, z1, z2, z3. And let's try S2. Maybe it's even easy for S2. S2 is equal to z1, z2 plus z1, z3 plus z2, z3. And now that's supposed to be a function of the Newton polynomials. Let's write it, F2 of the Newton polynomials. Of course, this function has to be, okay, here we go again. This should be easy. This should be alpha times the first Newton polynomial, which is this, to degree 1, squared, plus beta, it should be easy, of n2, right? And let's see if we can do it just for fun, to go home and get something to eat. This is alpha times n1 squared, so okay, here we go. z1 squared, let's see, 2z3 squared, plus beta times z1 squared plus z2 squared plus z3. Oh, it's great, I can do it. Even I can do this. Right? I hope when you square you get middle terms here. You get alpha times you get 2 alpha times z1, z2 plus z1, c3 plus z2, z3. It's easy to do in this case, right? Plus alpha times the squares, z1 squared plus z2 squared plus z3 squared. And now beta has to kill these things. Beta has to kill these things. Beta z1 squared, z2 squared, z3 squared. And alpha has to be 1/2. And so beta equals minus 1/2. I mean, it's very easy in this case, right? But you can imagine when it gets large, it gets really tricky, right? But it's the same thing. Okay. And I'm sorry I wasted your time with this last thing, but it's very interesting. Basically, the only question is to answer Martin's question, why this mapping is surjective. Okay. My answer is it's proper. It's very easy to see it's proper. Okay. But that's not a very good answer for you. Okay, see you tomorrow. Thanks for coming today. Don't get damaged by the wind. See you at dinner there.